We've actually sort of already talked a little bit about learning and memory in a few other chapters, right? We talked about the conditioned emotional response, right? That was an example of learning and memory. So you guys are already got some foundation here, right? Now there's a whole bunch of stuff here, some of which we'll talk about, some we won't. All right, what is learning, just in case you didn't know? It's acquiring new information. Exciting. And your experiences change over time, and that's going to make changes, actual physical changes to your nervous system, and then observable changes with your behavior, right? Memory is sort of this long-term change in your nervous system, right, that follows learning. So learning is one process, memory is the other, right? And so you've got to have both of these sort of going together. And here, I don't know, we'll kind of fly through some of this. Here is sort of the basic steps in learning, or learning and memory. You've got to encode, you've got to consolidate that memory. So once you've got that memory sort of there, you've got to make it take up as little space as possible so you can store it somewhere and then pull it back out whenever you need it, right? So you can kind of re-expand it. And that, I don't know. This is my big complaint about people who are like cognitive psychologists. Anybody a big fan of cognitive psychologists? Casey, are you gonna? You got to watch some of them, right? I mean, you do. They're just like, hey, check this out. Encoding. Put it in a box. I'm done. And that tells you absolutely nothing about how that process works. They're like, well, you've got an encoding process. It's like, yeah, my radio's got a knob that turns it on too, but that doesn't mean I understand anything about what's going on inside my radio just because I know it's got an on button, right? And so that's what I think happens here. We call it boxology, and we say that with as much derision as possible, right? It's boxologists. Because they, I don't know, it's important to try to fill in what's going on here, right? You want to know what are the squishy bits inside of that, what's that going on, right? And a few years ago, decades ago, half a century ago, there was this guy named Carl Lashley. Everybody who's named Carl, I call him Big Carl, I don't know why. I just think that's an appropriate nickname if your name's Carl, it's just Big Carl. Carl Lashley's cool. Casey, did I ever tell you he's my scientific great-grandfather? That's exciting, right? Carl Lashley had this awesome idea, right, for the ingram. And he was like, hey, if you remember stuff, there's got to be a physical place where you're putting it, right? And there's got to be something in your brain I can find that's like that chunk of memory, right? That's what that is. What was that movie with the guy with the marbles in the brain, and Lewis Black was yelling at people all the time? Does anybody know what movie I'm talking about? It's a Pixar movie, I think. I obviously saw it. Yeah. What was it? Did you Inside Out? Yeah, right? And so, I don't know, what was his name? Mr. Hufflepuff or whatever, I don't know what it was. You know, the funny guy, the imaginary friend.
Bing Bong.
Bing Bong, was that his name? Somebody's seen that movie more than once. So he goes and there's like all these memories right there. There's these like these discrete marbles, right? These like balls, and you're like, oh, there's, and you can like, you know, throw things around. And I think that's what Carl Lashley had in mind, right? Like, there's definitely like, I mean, not that there's like an imaginary friend running around in your brain, but there's like this definite one little spot that is the memory of the time in the third grade. You know, you got an F on your spelling test, right, or whatever. I don't know what you did in the third grade. I don't care. But there's that. But that's not really how it works, and we'll think about that a little bit later. Most of your memories are highly distributed throughout your cortex, right? And they're like little itty bitty pieces of these memories, and they're all sort of distributed amongst multiple synapses in this big network, right? And so they're really these distributed things. And so when you activate or you retrieve a memory, you're not plucking out that one marble, right? But you're plucking out little pieces of that marble all over your cortex, right? And that's kind of how things are actually stored. I guess at this point, I'm also required to mention this other guy. We'll talk more about Donald. Oh, that's an initial. Hebb, right? Hebb was sort of a brilliant guy. He was actually president of the American Psychological Association for a while. And back in the 40s and 50s, he was really doing some heavy work. He had this idea that, you know, how many of you have heard neurons that fire together wire together, right? That's a pretty standard thing. There's a lot of nuance to that. I don't know that Hebb actually ever said it. Maybe he did, maybe he didn't. But a lot of people pull that out of Hebb's work. Basically what Hebb said was, well, if you're trying to associate two things together, you're trying to learn some relationship, then it makes sense that the neurons that encode both of those things will probably be active at the same time, and there will be a strengthening of that connection, right? And that's what Hebb said. And what's really interesting about what Hebb was saying back in the 40s is that we have yet to really find a situation where he's wrong. We've added a lot of nuance to his ideas, right? We found a lot of interesting sort of wrinkles and details, but his basic premise is the same, right? If you activate two neurons at the same time and they're connected physically, the strength of that synapse actually increases. Now, he didn't understand the subcellular mechanisms behind that like we do now, but there is this synaptic strengthening process, and we're going to spend some time talking about that, so it's going to be a lot of fun. For those of you that have been waiting on ion channels since like chapter 4, we're going to come right back to them. It's going to be thrilling. We might even talk about genetics for a few minutes, and that's, I know, right? Just hope you guys don't get overexcited. I don't care about that stuff. Oh, we should talk about different kinds of conditioning. How many of you have heard of classical and operant conditioning? How many of you are actually taking a learning class right now? Like anybody in that class learning? Yeah, so I'm going to give you like a brief overview of it. He's probably, hopefully, giving you more detail than I am. If he's not, let me know and I'll take care of it. That's my job. Departmental enforcer. I don't know. Are they hiring? I don't think they're hiring for that. But if they were, I think I'd do well. So classical conditioning is your basic Pavlov. You guys familiar with Pavlov, right? This is like the biggest sort of like, oops, that worked out better than I thought it did. Situation, right? Pavlov had this brilliant idea, and I always think about this. What was he telling his family? What was he thinking when he said, woke up one morning, he was like, I figured it out. Dog salivary glands, I'm going to study them the rest of my life. I just don't know how that gets somebody excited. But that's what he was doing. He was studying dog salivary glands. He had a really clumsy lab assistant who like banged pans around every time he went to feed the dogs. What he noticed is he was sitting in the office one day, he was like banging pans around, and they had these devices, right, like kind of implanted in the dog's jaws that would catch the saliva. You know, it's like, whoa, man, that's like squirting out some spit right now while you're clanging those pans around. Why? And then they started like coming up with these other experiments. They're like, oh, let's give it some food, but let's ring a bell first. And then they would ring a bell and then give it food. And that's the story they tell everybody, right? Ring a bell, give the food, you ring the bell, then you get the salivary gland activation. They don't tell you all the other story behind that, right? That's really what happened. So that's classical conditioning, right? Okay. We talked about this when we talked about that conditioned emotional response, right? We talked about your older brother punching you in the ribs. We talked about being shocked, right? If you're a rat, you ring a bell, you're shocked. That's basically classical conditioning. A little bit after that, there were some other folks that came along. Hopefully, Brandon, he talks to you about, Dr. Lane talks about Thorndike, right? He talked about Thorndike. There's a real problem with Thorndike. He was like, man, that cat, every time I come in, look how it figured out how to get that open, and that cat's a genius. The problem is, what he didn't take into account is like, how many of you have a cat? Yeah, what does a cat do every time you walk into the room? Rubbing fur right on you, right? So obviously, that's what happens. When you walk into a room, a cat starts rubbing stuff, right? So it wasn't like the cat was like, man, that guy comes in, he's got fish, I'm going to open this cage. He was like, no, guy came in, natural instinct, I'm going to rub stuff. And it just so happened to open the door. So there you go. But Thorndike, all the same, was an important thing, right? And then you had this other guy, B.F. Skinner, right? And Skinner is probably one of the biggest guys that we think about when we think about operant conditioning, right? And Skinner was like, hey, let's put a couple of levers out there. Let's let a rat hit a lever. If it hits the correct lever, let's give it a treat. Guess what the rat's going to do? It's going to hit the right or correct lever every time, and it's going to keep getting those treats. That's operant conditioning. You have to do something to get a reward. You do the wrong thing, you don't get the reward, right? Or you could potentially get punished. Works the same way. I don't know what that is. I think that's a chair that needs lubrication. We could spend a lot of time talking about unconditioned stimulus and conditioned responses and all that business, but I don't really want to do that. I think it's important, but it's not going to make a big difference in this class, right? If it's unconditioned, that simply means that's the natural response, right? If you get shocked, you flinch, you jump back, that's unconditioned, right? Not a big deal. If I ring a bell and you flinch, that's got to be conditioned, right? Because normally ringing a bell is not going to make someone have that negative response, okay? Not a big deal. Reinforcers and punishers, don't get tripped up on this. A reinforcer simply increases the likelihood you're going to perform that activity. A punisher decreases the likelihood. People talk about, oh, what about positive punishment? What about that? That's just like slapping somebody. What's negative punishment? That's taking someone's shoes from them. It's still a punishment. It's still going to decrease the likelihood you do something. It's just whether or not you added something or subtracted something from that person's world. And reinforcers work the same way. What's positive reinforcement? Here's $10. What's negative reinforcement? You don't have to clean the house today, right? It's the same idea. Here's a fun gadget. What's kind of a natural reflex, right? How many of you have ever had an eye test? Yeah, I can tell which ones you have. If you haven't, you should go every 2 years, get your eyes checked. But one of the things they'll do is they'll put that puff of air in your eye, right? And they're gonna, every time that happens, what do? You close your eyes, right? And so if somebody puffs air in your eye, you're going to close. Right? And so we've kind of exploited that here. We got a speaker, it's going to make a noise, and then we're going to, bam, get you in the eye with a big puff of air, right? And what happens? Tone, puff, you flinch, right? You blink your eye. What happens eventually is if you simply play the tone, guess what happens? Your eye's going to flinch, right? You're going to blink, you're going to close your eye. Okay? Because you paired those two things together, classical conditioning. This is just like Pavlov. Operant conditioning, we already said what's going on here. There's lever press. The rat has to do some behavior. That's what's important between the difference between operant and classical conditioning. Don't worry about this stuff too much. We'll talk a little bit about what we need to later, but I'm not going to ask you too much about this sort of process. There are different kinds of memory, right? Again, if you're taking a cognitive relearning class, let's spend more time on this. Here's a shocker. You've got short-term and long-term memory, right? I know. Nobody was ready for that. Long-term memory, you've got a couple kinds. You've got what's called declarative memory, right? This is stuff that you could tell me about. And then you've got non-declarative memory. These are things you can't tell me about. Okay? So if you recognize objects, recognizing faces, right? How do you know that this particular person is someone you know, right? That's not declarative. You just look at the face and you're like, yeah, I definitely know that person, and here's who it is, right? Not a big deal. Types of memories, don't worry about that. Classical conditioning, we already talked about the amygdala, right? Later we're going to spend some time, I don't know if we'll get to that today, we might. Hopefully we do. Later we're going to talk about something called long-term potentiation, right? LTP. This is an important concept that we really need to think about. This plugs right back into those concepts that Heb was talking about, right? And in fact, we have a concept called Hebbian plasticity. Okay? And that concept of Hebbian plasticity is just that your synapses change over time based on experience and use of those synapses, right? And the process that has this happen is called long-term potentiation. Basically what we mean is over time, there's a strengthening, right, of particular associations, of synapses that are related to each other, right? And that way in the future, you can get an equal response out of that situation with less of an input, right? Because it's a stronger connection, you don't have to put as much in to get the same response. Okay? So just kind of keep that in the back of your mind. We'll add some more to it later. All right. So we already talked about conditioned emotional responses, right? We talked about the tone and the stimulus, right? So this is like the air puff. Okay. They're both going to land on that cell in the amygdala, right? And over time, as these two inputs are both coming in, they're coming in, they're going to get stronger and stronger and stronger. This guy here for the tone is going to get so strong, right, at some point that you're not going to need that air puff. You just get the tone. It's going to be strong enough on its own to activate that amygdala cell, and you're going to get that emotional response. Okay? Now that's interesting, right? Because you think for a moment like, well, I mean, who really cares about like an air puff and a sound, and right, that doesn't really matter. And there's sort of this interesting concept. Some people call it prepared learning. Has anybody heard of prepared learning? Right? I'm not a big fan of that term. Casey, do they still use this out there in the world? Prepared learning. You've never heard of prepared learning? That's disappointing because you've actually been in this class with me now. This is the second semester.
Other than that.
Oh, okay.
But,
I like the term better, ecological learning. Which is kind of cool, right? And the guy who figured this out, his name is John Garcia. And it was Garcia's rats. He had these rats. And Garcia had this really interesting thing he could do. He could make rats vomit. That's a real skill. I mean, it is. He can make rats vomit. Super cool, Mary. Really is. What was interesting about this is he had sort of two situations, right? So he had some water, but he had two kinds of water, right? He had what he called noisy water, and, I'm sorry, not noisy water, sparkly water. And then he had tasty water. Okay? So he had sparkly water and tasty water. Right? So what would he do? He had a rat. The rat could drink water. If it was sparkly water, he had some lights flashing. So that's exciting. So these lights would flash, the rat would drink the water, whatever, not a big deal, right? Now with that sparkly water, he had two choices. Shock or vomit, right? So not only could he make rats vomit, he could also make them, he could electrocute them, right? So he's got two skills. So they would drink this sparkly water, right? And he would either shock them or he would make them sick later. He put a chemical in the water, and when they would drink it, they would vomit later, right? And it was a tasteless chemical, right? So it was just water. What was interesting with these rats in this sparkly water situation, if he shocked them, guess what? They stopped drinking sparkling water, right? Next time they saw the sparkles, forget it, we're not drinking that water. If he made them vomit, they didn't really care if there were sparkles, if there were lights. There were still lights. It was like, oh, I'm going to go back and drink that water. Okay? I know you're thinking, like, stupid rats, right? I mean, you got shocked last time. Why would you do that? Or you vomited last time. Why would you do that? In the other group, with the tasty water, again, you had those two conditions. But the reverse happened. If they received water that had a flavor additive, and they were shocked while they were drinking that flavor added water, they never learned that association. They never learned that the taste and the shock went together. Okay? But they did learn that the taste and the vomit went together, right? So when they vomited, even 24 hours later, they were done with tasty water. Next time they went up and they licked the tasty water, they were done with it. Okay? If you think about a rat for a moment, so just imagine you're a rat. We'll make an improv activity, right? For those of you that took acting lessons. So take a few moments to think about a rat. Think about the things in a rat's life, right? What is something in a rat's life that's dangerous is a cat, right? And a cat really is like a visual stimulus, right? If you see a cat, you're going to feel physical pain, right? The cat's going to bite you, it's going to scratch you, right? And so a visual stimulus like sparkly water would lend itself to some sort of painful tactile experience, right? That shock. Seeing a cat is not going to make you vomit, right? If you're a rat. So there's no reason why that visual stimulus should be associated with a gastrointestinal issue, right? Okay? The reverse is going to happen. If something has a flavor to it, well, why would it cause you physical pain? It's not going to, right? You eat a cheeseburger. That's not going to make you, it's not going to shock you, right? But it could make you vomit, right? Because it's, again, sort of a food ingestive, digestive related issue, right? So what's interesting about this is Garcia was able to show we're not able to make every single pairing possible, right? It's impossible in this particular situation to make a rat stop drinking sparkling water if you make it vomit, right? It's not, in sort of older terms, prepared to learn that, but for our thinking, its ecological situation has not created the opportunity for it to evolve to make that connection, right? So there are limits on the things that you can pair. I don't know, I think it's pretty fascinating, right? You can go home and do this if you have a rat. Anybody have pet rats? How many of you have rats and you don't know it? That's everybody's hand should go up, right? They're all over the place. They're probably crawling around right now on the walls. They might fall down on you while you're taking an exam during finals week. All right, questions about this, about Garcia's rats? That story's not in your book, unfortunately.
So what reference did you use then?
Garcia, 1972. I don't know if that's the right year. I would check that year. I think it's close. Anybody want to look up Garcia's rats? Who's got a Google box? Nobody. Keely's watching. She has you have your laptop out and you're just going to watch Mary look this up. You could have already typed in Garcia's rats. Nothing bad's going to, I think nothing bad's going to show up on your computer. Now I'm worried.
1955.
55. Not even close. Not even close. Yeah, and it was a long time ago. Is that better? There are other places you can find stories about Garcia's rats. It's a very important story that I unfortunately don't think is as well distributed as it should be. Usually you get Garcia's rat stories in animal behavior books. You don't get them in books about learning and memory. Kind of interesting, right? So there you go. So you have to read 2 books. I know that's a real pain for you. Having to read that extra book, right? What are you going to do? All right, so this thing called LTP, who remembers that? We just talked about it briefly. We said it was long-term potentiation. We said it was a way to make a synapse stronger, right? So that that lower input can come in and get that bigger response, okay? Guess what? It happens out there in the amygdala, right? And it happens because, one, we're going to be activating that NMDA receptor. Now, this NMDA receptor is for glutamate. Who remembers glutamate, right? That's that excitatory neurotransmitter, right? Super awesome, okay? The cool thing about NMDA receptors is they have two points to them. They're ligand-gated, right? We already said they're glutamate, so that ligand is glutamate, right? Just like any other receptor that needed dopamine, needed serotonin, needed acetylcholine to open that, these guys need glutamate. It's not a big deal. But they're also voltage gated. And what we mean by that is the neuron has to be depolarized just a bit, right? It has to be excited a little bit in order for these guys to open. Even if there's glutamate present, you've got to activate them as well, right? And that other activation, where does it come from? It comes from that other synapse, that other cell, right? That's coming on there and it's kind of raising that membrane potential, right? So we're kind of giving that boost to it. I like to think about this voltage-gated business as like the assisted chin-up machine, right? Anybody use that, or the assisted dip machine? You guys know what that, right? So it has like a counterbalance on there, right? So that you can move your body up and down, right? So you can kind of select that. So we have to have a little bit there to help you at first, right? Get you moving, then eventually you can reduce that counterbalance. You can move yourself up and down on your own. That's long-term potentiation if you were a weight machine. There you go. That's all you need. Just when you take your exam, draw this. You gotta have the stacks of weights here, and then you gotta have like the platform for your knees, right? And then for your arms, and then like something goes up, and you draw a person on there. I failed art class. There's the other foot. Oh, and it's probably got like something there. And then there's always like somebody over here watching. He's probably got on an obnoxious hat or something. I don't know. That's what I imagine. Anybody wear hats when they work out at the gym? No. You wear a hat all the time though, right? I mean, that's like part of your chosen profession. So that's different. But I think about these guys at the gym who wear hats. I think like, I sweat at the gym. I'm just going to ruin a hat. This doesn't make any sense. You can't really wash a hat. You just got to buy a new one. Can't wash hats. Blakely, do you wash a hat or you just buy a new one?
Wash it.
Oh. Let's buy a new one next time.
I'm cheaper.
I think maybe I shouldn't dry the hat. I think that's where the problem was.
And dry it.
Yeah, because it didn't fit after. I did it for like 4 hats, and I was like, what's the problem here? All right, hey, check this out. This is awesome. This is LTP, classical conditioning. Don't worry about that too much, right? You've got your NMDA receptor. Remember the time I told you about the NMDA receptor, right? What does it do? It's got 2 things. Voltage gated and it's ligand gated, right? So that's helpful. When it opens, what happens? This big guy comes in, calcium. Why is calcium awesome? It's a 2+, right? You got 2 sort of positive charges coming in there, so that's like super cool. Before that happens, though, you got this guy here called magnesium. You got to bounce him out of the way, right? That's kind of what that voltage-gated business does. It'll shoot that magnesium out. You get your glutamate on there. Your calcium comes in. Okay? Calcium is awesome because not only does it give you that 2+, calcium can activate sort of downstream processes, right? If we want to make a synapse stronger, right? What is the only thing I've ever talked to you about that's at a synapse? Receptors and ion channels, right? And if I want to make that synapse stronger, if I want to make it more powerful, if I want to make it work better, we just add more ion channels, right? So if we add more ion channels, it becomes stronger, okay? Because the more ion channels there are, the more opportunities I have to open, even though I'm only dropping a few molecules. Because remember, we said it's usually not the neurotransmitter itself that's the limiting factor, it's the number of receptors that you have, right? The number of receptors is typically the limiting factor at a synapse. Okay? So if you add more receptors, more ion channels, even though you're dropping the same number of molecules, right? You always have more molecules of neurotransmitter than you do receptors. Okay? So calcium starts this downstream process, right? We'll talk a little bit about that later. And the end result is something called an AMPA receptor being inserted into the synaptic membrane. The AMPA receptor also runs on glutamate and allows sodium in. Okay? Glutamate binds, sodium comes in. Now, because we're after the process here, right? Now, not only do we have those original NMDA receptors, but we also now have our AMPA receptors. So guess what happens when I drop that same number of glutamate molecules? I activate a glutamate receptor, and I can activate an AMPA receptor, an NMDA receptor and an AMPA receptor. They're both glutamate receptors. So I can get more ion channels that open, right? I can more easily take that membrane potential, because remember it's down around negative 65 millivolts. I got to depolarize that. I can do that more easily if I have more ion channels to allow those ions to come in. Right? Does that make sense to everybody? Who's got questions about that? Awesome. So this is sort of like, this process is sort of like muscle hypertrophy, right? So you're just making things stronger. You're physically making a change in the synapse structure, right? so that it is stronger later. Just because I haven't mentioned him enough yet, this is when I should bring back, this was the idea Donald Hebb had, right? This was his whole concept here. So there you go. Well ahead of his time. I think he even predated Garcia's rats. Because I think it was like 1949 when he gave his, he gave a speech called, what was the title? Psychology as a Biological Discipline, and he gave that to the American Psychological Association back in the late 40s. So. And then some people said, oh, that's stupid, and they ignored everything for a long time. And now they're paying the price for it. How many of you are psych majors? Change your major. Right, Casey, am I allowed to tell them that?
Sure.
I probably have access to some of your records. I can change it for you. Just write your 901s on a piece of paper and I'll take care of it. Casey, why are you giving me that face?
I would anticipate that the department kind of expects those.
Yeah. I mean, you've got too many students as it is and not enough faculty, so I got to run some people off. I'm just doing a service for the rest of my colleagues.
Fair.
Right? I'm going through a side story in my head now, deciding whether or not to share it with you, but I don't think I am, so we're going to move on. It was a personal rant about something that doesn't really matter. I mean, it matters to me, but not to you. You're curious? So they're like, how many of your psych majors again? Yeah, they're like 450 of you, right? How many of us are psychology faculty? Yeah, so I'm gonna rate. You can do this with your arm if you want, Case, because you're like a part-timer, right? So you kind of count to our full-time equivalency calculation, right? And I think there are like 20 of us, right? Like if you look at everybody in our department, there are some departments who have like I'm not gonna call out a particular department, but they have like this many of you and that many of us. And I don't know if you can like do math, but I can, right? That's why I decided not to go into that, and I came over to this. Actually, I went to something slightly different than this over here. Something doesn't work out the same there, right, Keelan? So I got to run some of you off, so I can bring this down to closer to that. Because they're not going to give me more here, even though they're doing this. I'm going to tell you, none of that's going right there. Just to let you know. Is that true, Casey? I can tell them that.
Yeah.
You ever wonder, like what percentage of their tuition actually goes to my salary?
I'm sure you won't think
I think about that sometimes, right? Because I think they'd like to know. I think you as a student would like to know what percentage of your salary is actually going to pay the people who are giving you your education. Right? Because I'd like to know, like, how much. Some of your salary's got to go to the president. He's got a job. Some of it's got to go to the provost and the vice presidents and the people who work in physical plant. Right? It's got to go all these places. But I'd love to see the breakdown of where your tuition goes.
Statues.
Huh? Statue. My favorite one is the one right there on like 4th and Hal Greer, the big giant green M. Because I thought, you know what we needed right there? Something that let people know. We're on Marshall University now. Because nobody knew that before, right? The big gate that says Marshall University, the big building that says Marshall University.
Or the sign that's on the flower bed that says Marshall University.
The other signs, the fact that it just is Marshall University and everybody here knows it. I don't know why we needed that big giant M. I don't know why.
It's iconic for PR.
It's what?
Iconic for PR.
Iconic for PR. Yeah, I guess. What I liked better was that bison that like some guy donated who was a former student that's made out of recycled aluminum cans. That one was
I
okay.
didn't know those was recyclable. That's cool.
The one there,
Down the street.
wherever it is. Yeah, not the big ones, like the big 3 running, but the
There's more than one.
little thin one that's on campus
Oh.
with the flowers around it. I don't think he donated the flowers. It was it's like a student who was a veteran and he wanted to have something that was kind of like, for veterans. So there you go. I mean, I'm okay with that.
Yeah.
The big green M, I don't know. That's a sore spot for me too.
Can you go back to the previous slide for a second?
Oh, wrong way, sorry. I really meant to go back.
Isn't it the NMDA receptor that allows calcium in?
Yeah, what did I say? Yeah, it's right here, NMDA and calcium. Is that cool? AMPA lets in sodium. Is that better? All right. What about the basal ganglia? Don't worry about the basal ganglia. Although, if you knock out your basal ganglia, you have you lose the ability to do motor learning. So that's kind of interesting. Don't worry about too much else. This is a fun one. How many of you have ever done something more than once? Yeah, and you did it that second time because it felt good the first time, right? Like studying. How many of you have ever done that more than once? I'll know, right? I can tell. You should try it sometime. I know there's like a delay between what you're doing and when the reward is, but trust me, it's going to be there, right? So there are two brain regions, and we've talked about these briefly before. We talked about the ventral tegmental area, and we talked about it when we talked about maternal behavior, remember? And I said, your mother doesn't love you, she's just addicted to taking care of you, right? Because the same brain circuit that gets activated for addictive behaviors is the one that gets activated for maternal behavior as well. But the projection from the ventral tegmental area to this guy called the Nucleus Accumbens, right? This is the brain circuit, right? That is involved in reinforcement. If you do something and the ventral tegmental area dumps dopamine onto the Nucleus Accumbens, you will enjoy that activity and you will do it again. It's that simple. There's no real way around it. Guess what happens when you do cocaine? Yeah, your ventral tegmental area dumps dopamine on your Nucleus Accumbens. And guess what happens? You do cocaine again, right? Guess what happens when you win a marathon? Yep. Your ventral tegmental area will dump dopamine on your Nucleus Accumbens. Guess what you'll do? You'll continue to run, right? You'll continue to try to win another marathon.
You know how they say that once you do a certain drug, then you'll constantly be chasing that first high? Right? That's what I was told?
Yeah.
Am I crazy?
No, I thought there was a question there.
There is, I'm just saying.
Okay, I'm just waiting on it. Just waiting on the question.
I'm saying that, like I'm not just making it up. Is that due to like a different size or amount of dopamine being released?
I honestly think I think that's a little more subjective than anything else. I would also, the problem with most drugs, right, is yes, they may make you feel awesome, right, because they give you that big rush of dopamine, but like methamphetamine, right? You take some methamphetamine, you're definitely getting some dopamine. If you continue to take methamphetamine, you're definitely losing some teeth. So
I heard that wasn't actually from the drug itself. Is that true? It's just like people forget to brush their teeth.
well, there's a whole host of things that can.
I don't know. That's
Yeah, I mean, obviously your hygiene's not the best. There's secondary infection issues you're worried about. There are a ton of things going on. But their point is there are negative consequences, right? And the more you do a drug, the more likely you're going to have those negative consequences later. So that's going to be, there are going to be some negative things associated with the positives. So, I mean, if you took a drug once and you had a nice, like, positive experience, you didn't have any side effects, you might, well, I'll try that again. But then you're just going to get it, like, deeper and deeper in this loop, right? And there's actually some, like, the problem with things like drugs, and we'll talk about drug addiction and things later, we'll have a chapter on that, is that the effect of the drug is rather short-lived, right? So if you take something, it has, like, a limited amount of time that you're actually going to feel that experience. And then the more and more you do that, the stronger that craving becomes, and so the stronger your sort of negative feelings in between are, right? So you're constantly having this like, I need to get back to where I'm at that state because I can't stand where I am now. right? Because you're having like some negative feelings, and a lot of it's related to like tolerance and withdrawal. Without getting too much into that, because we are going to talk about that in a few weeks. We talked about it a little bit briefly before. That's really, I think, what's going on there. Your tolerance mechanisms are kicking in, and whenever you're not taking the drug, you're in acute withdrawal, right? You're in that experience where it's sort of a bad thing. Most of you have probably at some point tried to like limit your caffeine intake or something, and you've experienced like some acute withdrawal from that. And it's not pleasant. I mean, caffeine's like, yeah, whatever, you're kind of done with it. But if you're on something like methamphetamine or heroin or something more actively kind of works this system, it becomes a little more complicated. Does that make sense? Did that answer your sort of question?
Yeah, it's not really about the amount, it's about the simplicity. Like in the beginning, it was easier because you haven't faced those consequences yet.
Yeah, and I think actually you will release less dopamine as you.
What is it?
You'll release less dopamine in response. I mean, not necessarily release less, but the effect of the dopamine is it will lessen over time because of tolerance as well. So that's why people have to increase their drug use over time, like the amount of drug that they use over time, because to get that same amount of dopamine or that same effect, you might still be releasing dopamine, but you might have removed some of those receptors. You have to have more of the drug, and then increases likelihood again of secondary or of side effects. All right, don't worry about that. It's a rat brain. This is pretty simple. Basically, a rat pressed a lever, and somebody stimulated its ventral tegmental area, and then someone measured the amount of dopamine. Every time they press the lever, lots of dopamine. They do this thing called microdialysis. I don't know if you guys are familiar with that. Basically, they can measure the amount of dopamine that's in the brain fluid right then, kind of in that interstitial space. Not as cool as like fast cyclic voltammetry. That's a little different process also. It's incredibly hot up here.
We should all leave.
Oh no, I don't think that's a good idea. I mean, like OSHA's not going to come in and tell me it's too hot. So I think you guys are fine. So yeah, now the breeze is picking up, so it's fine. Can you guys feel that in the back? Kyle, that's even worse than your normal disgruntled face. I mean, like you've normally got a disgruntled look, that's even worse. Huh?
It's hot.
Yeah. I'm not the one who told you to sit in the back.
It's scary, so I stay back.
All right. Don't worry about this. We talked about motor learning, perceptual learning. I'm not going to ask you too much about this. I don't know. Here's a guy looking at somebody sitting on a couch. That's interesting, right? Don't worry about it. I mean, really don't. It's all perceptual learning stuff. I'm not going to ask you about it. I might ask you about the hippocampus, but we'll talk about that in just a moment. All right. So the hippocampus is sort of an interesting structure, right? It's kind of rolled up like a seahorse. That's what hippocampus means, in case you're curious. Really plays a role in forming declarative memories and even modifying memories as they're being formed, right? So the hippocampus is not a storage location, right? I want to be clear about that. You're not storing memories in the hippocampus. Your hippocampus is simply retrieving those memories and playing them for you, right? What's interesting about that is you can modify those memories. You can pull them out, you can edit them unintentionally often, and then you can put them back, and the next time you pull it out, you're like, oh, I'm definitely remembering this. Things can be different, right? How many of you have remembered something that actually did not happen to you? Yeah, I mean, you don't have to like own up to that, right? But it happens. A lot of times it happens with like family stories. They tell you about the time when you were 2, you did the school jumping jack thing or whatever, and you're like, yeah, I definitely remember that. You probably don't. Most people don't remember things before they're like 4 or 5 years old, so you probably didn't remember it, but you've heard the story so many times, you're like pulling out memories of the time you heard the story about the time you did it, right? And you're just like, I'm putting it back just like I did it. And that happens, right? There was someone a number of years ago. How many of you have heard of Elizabeth Loftus? I think if I give a learning and memory lecture, I have to mention her, right? Anybody know Elizabeth Loftus? Probably talked about her in some of your other classes. She did you know her? I met her, she's nice. Yeah, no, she's super nice too, which is surprising. Yeah, it's surprising because, like, you know, she's probably one of the, I mean, she doesn't have to be nice, right? Like, some people have to be nice because they don't have anything else going on for them. Oh, what was that? Somebody groaned. I mean, do you sit in the same seat every time?
No, it was like a couple one down was the really squeaky one. This is a different one.
So, I mean, at some point, you know, we have to look at the common denominator here. And I'm just...
I thought correlation didn't equal causation.
They don't, but we can scientifically sort of start to eliminate other potential causes, right? And we can test this. We've got a hypothesis based on an observation. We should do a real study now and just have you sit in every seat and see what happens. But we need to test it before with the control group, right? So this is going to be, instead of between subjects, it's a within subjects test. The chair being the... So we can do this. So Elizabeth Loftus, again, she's probably one of the most preeminent memory researchers ever. So she doesn't have to be nice to people, right? But she is anyway. So there you go. Just keep that's an important lesson for you guys. Sometimes you have to be nice if you don't have anything else going on. What she would do is she was one who worked on the what do they call them, Casey? When you convince someone that something bad happened to them and they put somebody in jail for it. Yeah.
Eyewitness testimony?
She did eyewitness testimony and false
memories.
False memories, yeah. Yeah, false memories. There was actually a cool sort of benign study of this, right? So they would have someone come in and they would say, hey, tell me 3 things about somebody in your family. All right, I'll tell you 3 things. And then they make up a 4th thing. And then they'll bring that person in and they'll go like, hey, here's 4 stories that so-and-so from your family told us about. And they're like, oh, okay, that's interesting, whatever. And then they ask them about it like weeks later, and the person can't determine, like they report all 4 of those stories as if they actually happened, even though only 3 of them happened. So it's really sort of a fascinating thing, right? And I'm going to tell you the worst kind of witness ever is an eyewitness. Don't trust an eyewitness, right? There are much better witnesses. There's the DNA witness. I love the DNA witness. Also the electronic witness, right? That's a little bit more trustworthy. You got it on camera, and you got it on DNA. That's what you trust, right? Don't trust eyewitnesses. Because, I mean, you guys could go rob somebody later, and I'm you all with the same thing. So I'm just going to go, yep. There were eyes and a nose, and I think some hair, and maybe an ear or 2. That person right there is who did it. Eyewitnesses are useless. Okay. And Elizabeth Loftus was big on it. The other thing she did, which was kind of a cool study, she did this like car crash study. I mean, that's a cool one, right? So she was really big about like investigation techniques, right? Anybody criminal justice major? Yeah, there you go, right? Did they talk about Elizabeth Loftus ever?
I'm not sure about the names, but I know about the crash.
Yeah, where they would like show a picture of a car accident and she would say, tell me how fast the first car was moving when it smashed into the other car. And then she would say to another group, tell me how fast the car was moving when it bumped into the other car. And the damage was the same in both pictures. It'd be like 85 miles an hour, it'd be like 6 miles an hour. It's like a huge difference. So there you go. Next time they talk about it, just stand up and scream Elizabeth Loftus. Please. We would all appreciate that. You want to practice? You want to practice? You want to do it?
I'm good. You know, I graduate in May, so I don't think it's going to come up anytime soon, so...
When you walk across the stage, you should hold up a sign that says,
Just steal the
I was
mic.
here. Just spill the mic.
I didn't drop it.
Yeah. And no one will know if you did it or not because eyewitnesses are horrible. Right, Casey?
Yeah.
I mean, this happens all the time. How many times have you seen on television, some guy's been in jail for 20 years for some crime, and they're like, oh, yeah, we did some DNA, and I guess you weren't there. Sorry. For God's sake. You know, it happens all the time. I mean, it really does. People are thoroughly convinced somebody else did it, and then the DNA exonerates them. There you go. So that's Elizabeth Loftus. Fun story. Don't worry about this stuff. Those are just types of memory. So, consolidation, reconsolidation. We're pulling those memories out. We're putting the memories back in. Right? Hippocampus is involved in that. Also, the hippocampus is involved in like spatial memory as well, right? So there's the Morris-Water maze, okay, and also what we call a hippocampal place cell. So there was a group a few years ago led by Maybrit Moser and her husband at the time, Edvard. These folks actually won a Nobel Prize. Who's excited or disappointed, I should say, that Paul Greengard died? Anybody know about Paul Greengard? He's the guy who figured out that your brain uses chemical signals. He won a Nobel Prize for that too in the early 2000s. He actually just died. He was like 93. Him and Eric Kandel, they shared the Nobel Prize a number of years ago. We'll talk about Eric Kandel. Great segue, actually.
What was that last name?
Huh?
Scratch up there. What's that last name?
Greengard?
Up there.
Oh, Moser. M-O-S-E-R. Yeah, sorry.
Did they do the water maze?
They didn't do the Morris-Water maze. They did some other things where they were looking at hippocampal place cells and things called grid cells. And basically what they discovered was the way that your hippocampus creates a map of the world as you're moving about it. And they did their studies in rats. And so they looked at these hippocampal place cells and the grid cells in rats on the mapping process, which is kind of interesting. So as the rat would move through its environment, like different cells, and they would kind of be activated in a sort of a sequential spatial pattern, which is kind of exciting. Yeah, I think they got the Nobel Prize in 2012. That might not be right. Jacob's going to look it up.
Yeah.
Yeah. You can tell us next week. Fine. Hippocampus is important for that. There's actually, and I think this is not so true now, but it used to be true that taxi drivers had a larger hippocampus than non-taxi drivers. The reason I don't think that's true now, and I know you're kind of like making this weird face, right? Previously, what did taxi drivers have to get you around town? They had to have a good understanding of streets, the town, right? And they had to know things. What does a taxi driver need now to get you around? Yeah, right? So you don't even need to know anything. Right? So how many of you have ever been in a taxi, Uber, Lyft, and you get in and the guy's like punching things in, right, on his phone. It's like, all right, I'm going to get you there. That guy's hippocampus is no bigger than yours. But if you get in and you're like, hey, take me over to wherever, he's like, got it. And he doesn't need his GPS. That guy's got a big hippocampus. I don't know if a big hippocampus gets you excited or not, but that's a good way to figure it out. Everybody's got different tastes. Some people are hippocampus people. It happens. So here's the Morris-Water maze. This looks really fancy, but in fact it's probably just a kiddie pool that somebody spray painted. Right? I mean, that's really all it is. And then they put a platform in here. And then they drop the rat in. Rats hate swimming. They just hate water typically, so they're going to try to get out of there. They're going to get over to the platform, which will be awesome. If you lesion the hippocampus, what the rat will do is get lost. So if you have a normal rat that's here, you've always got your finish, your platforms in the same place. You drop your rat, it's going to take a short path to get over there to the platform. Once it figures out where it is, it's like, awesome, I've got it, no problems. With the rats that have hippocampal lesions, drop them in, first time they'll find it, then you do the lesion, and then they're just all over the place. Even if you drop the rat right next to the platform, if it can't see it, just take off, Scotty. I mean, it's just, there you go. So that's a real problem, obviously, for the rat. So you got to have a hippocampus, so you know where you're going. You can have a memory of that. What about amnesia? We should talk about that a little bit. There are two kinds: anterograde, which means you can't learn anything new, so you can't learn anything going forward. And retrograde, you've forgotten everything in the past. If you ever get to pick, always pick retrograde, right? Never pick anterograde, because you want to try to remember new things, right? That's great. But with retrograde, you can forget all the stupid stuff you used to do. You can just make up great stories about yourself in the past, and it's good to go. Also, if you ever went out of a relationship, you can fake retrograde amnesia, act like you don't know who that person is, and just really throw a fit and get your stuff and move out. Anybody ever tried that? Anybody want to try it? Yeah. There you go, right? You got an excuse now. I don't know anything about what happened to me before 5 minutes ago. Who are you? I'm taking my stuff and leaving.
I think there's movies about that, and they like call them everything and stuff. I think that's how most movies are.
Really?
Consolidation.
Yeah.
Oh, yeah.
That's not even close to the best Adam Sandler, Drew Barrymore movie. And I wouldn't even say The Wedding Singer was a great one. Yeah, I'm a big Wedding Singer fan back there, I know. The best Drew Barrymore, Adam Sandler movie was that time I watched Firestarter and then followed it up with Happy Gilmore. Nobody remembers that.
Billy Madison.
Billy Madison, I guess. Anybody seen Firestarter other than the two of us? I don't think so. Anybody know that was a movie with Drew Barrymore in it? No. Hey, spoiler alert, she can start fires. Didn't know that was coming. So there you go. Hey, how many of you have heard of this guy called HM? Anybody? How many of you have heard of this guy called HM? Anybody? No. How many of you have heard of this guy called HM? There was a problem with this guy HM. He couldn't make new memories. He forgot he did stuff all the time. He actually had temporal lobe epilepsy, and they had to pull out both of his temporal lobes. It took his both hippocampi with that as well. What was really interesting is probably this guy is the most important guy in the history of studying learning and memory. We've learned more about how your brain works from this one guy than probably just about anything else anybody else has done, especially in regards to learning and memory. What was really interesting, he died a few years ago actually, and they of course live streamed his brain dissection. It was exciting.
They're actually.
Right? I think there's a YouTube video of it. Yeah. No, it wasn't a joke. I don't know. I would recommend you do it. If you guys ever have like a weird brain thing going on, just live stream that brain dissection when you die. Sign paperwork.
My mom uses her brain aneurysm.
She what?
She had a brain aneurysm rupture.
Yeah.
She uses it sometimes as an excuse.
See, now you know, but you see.
I know what she's doing.
Yeah. You're well informed.
Yeah.
It's the only reason you took this class. This guy HM, what he would say is, he said he always felt like he was like waking up from a dream because he wasn't able to have that long-term memory to remember like, how did I even get here? He just kind of like knows I am here now, and that's fine. He knew like his family, right, from the past, but he just couldn't, like, they moved and he never could remember where his new house was. He'd go to his old house, but he couldn't go to his new house. He would read, I guess this would save you money on books. He only needed one book. He could only read a paragraph. He would read a paragraph and then forget what it was about and have to start over. I don't even guess he really needed a book. He could probably just, give him 4 or 5 lines text and he would be fine. I don't know what he would do if he was ever watching, like, can you imagine watching, like, you should think about watching, like, sports like that, right? Like, can you imagine, like, I don't even know, what sport are we playing again? Wait a minute, who are these teams? I don't know. It's the same game. It's a problem, right? Now, retrograde amnesia, on the other hand, you're fine going forward, so you can make, like, all new memories. It's just that old stuff you don't remember. So you can kind of just like, oh, I guess that's what happened. I'll take your word on it and just move on. Korsakoff syndrome, this is if you're a severe alcoholic. It's typically you see it in alcoholics, not really anybody else, but it's a vitamin deficiency. Oh, there's HM. We already talked about that. Don't worry about that. And don't worry about this. more of the same. Hippocampus is important. Okay. Here's a regular brain. Here's HM's brain. See those two big holes? That's where not only his hippocampus, but the rest of his temporal lobes were. You can imagine he had some problems. If you lose that much in your brain, something's not working right. All right, and there he is again. You should have stuff down here. You should look like a jelly roll. We already talked about this. Spatial memory grid cells, place cells. Talked about that. That's awesome, right? We should talk about this stuff. We already talked about LTP. How many times have I said that one now? 4 or 5, right? It's long-term potentiation. My assumption is, because I've said this several times, Casey, I might have that on the exam, right? Just think about it. Okay. There he is, Donald Head, right? Again, this is that cellular mechanism, right? Where we're going to strengthen a synapse. Okay? It's a pretty straightforward process. Let me go to a good diagram for you here. The end result is going to be that stronger response, right? So if you take that one cell and you activate it, and you try to measure in cell number 2 what's going on, you're going to get a little bump. If you then activate that third cell, at the same time you activate the first cell, you get a bonus, right? You get that potentiation. You do that enough, what happens is over time you don't need that third cell anymore, and you can still get that big bump. Why? Remember when we only had NMDA receptors? And then what did we do? What did we do here? Right? We added some AMPA receptors. Because we have more receptors, we can allow more positive ions to come in. When you let more positive ions come in, guess what happens? You get more of a depolarization. Now this is a population EPSP, right? And what that means is that's an excitatory postsynaptic potential from several neurons, right? Not just from one. We're looking at several, so we're measuring from a number of neurons here, right? So we're kind of activating several at once. Concept 6. Questions about that? All right, so this is showing you the, what we call summation, but remember that time I said that NMDA receptors are voltage gated? We've got to get that postsynaptic membrane up to a certain voltage before we can get this magnesium expelled, right? And what you need to do is you need to have sort of, usually at least 10 hertz. Rate of stimulation, right? So what happens is if you sort of stimulate that cell, and then it's going to drop back down, and then you stimulate it, and then that membrane potential drops back down, right? That population EPSP keeps dropping down. But if you stimulate it fast enough, right, you can kind of ride that wave up and up and up until you reach that voltage threshold so that you can expel the magnesium. Okay. Don't worry about this diagram too much, it's a little confusing. Here's your NMDA receptor. You've got magnesium in there, calcium's waiting on the outside. You've already got your glutamate in there, okay? So it wants to open, but magnesium's in there. What you need to do is, again, get that 10 hertz stimulation going. Okay. Expel that magnesium, allow the calcium to come in. Once the calcium is in, right? Calcium can start doing some cool things. Okay. And calcium is going to activate this downstream process. Okay. I don't want you to think too much about it because it's a little complicated. The calcium activates that downstream process that eventually takes those AMPA receptors and relocates them to the synapse. So the next time you have a stimulation come through, and you drop off some glutamate molecules, you now have more ion channels that you can open. Does that make sense? And that's it. That's for the long-term potentiation. It's not that complicated, right? There's also long-term depression. Sort of just the opposite, right? After a while, if you're not having any stimulation come through, these AMPA receptors will sort of disappear. They're not going to stay out there forever, right? Because you've got those synaptic vesicles coming in and recycling things in and out. Such. All right. Questions about that? Comments, concerns?